My name is Ruby Harris and this is Grace Bolton, and today we are going to present to you our Report 5 analysis video. So let's get started. First, picture this. You're a kid and you have your best friend in front of you who's also your worst enemy, and there's a basket of balloons between you and your enemy, water balloons. The question becomes, how wet can you possibly get your opponent? Now, just regarding aim and all those, small things, we wanted to answer this question, and so Grace will introduce our experiment design.
Our question of our experiment is, what surface gives you the largest splash diameter when a water balloon is thrown upon the surface? For our experiment, we have two factors, and we use blocking. Our main factor that we wanted to measure was surfaces. As you can see, we threw against cement, dirt, and rocks. And our nuisance variable that we controlled for through the blocking is the fullness of the balloons. And we filled them small, medium, and large. We used a sample size of 30 for our experiment, and we grouped the balloons into groups of 10 by fullness for our blocking. We measured F statistics. Ruby's going to explain how we conducted the experiment and limitations.
So we conducted the experiment by randomizing the surfaces with the fullness, and then we threw the balloons against that surface and recorded our results. So some limitations were like the force of the balloon being thrown, maybe like the angle of impact, some differences in like the dirt and the rocks, like how large were the rocks and that kind of thing. We were able to control for force pretty well by having Grace throw all of the balloons with relatively equal force. And we tried to do it as vertical as possible to eliminate possibility of angle impacting the results.
And then how we did this. We used a hose attachment, bunch of balloons, and it fills up all the balloons at the same time, which helped give us equal fullness.
Yes. So we did two major analyses. We did permutation and bootstrapping. For permutation, we created a custom function in our R code. And for that, we basically just shuffled the surfaces with within the groups. And we did this 1,000 times to create a distribution of our F statistic in that.
And then for bootstrapping, similarly, we did it 1,000 times. We resampled the data, taking samples with replacement 1,000 times. And again, this is with replacement and without replacement. Ruby will now show some visualizations of our results.
So here are some visualizations of our results, as Grace just said. We have two graphs here, and these are the graphs of just one run-through of our code. We would get slightly different graphs and slightly different numbers per run-through because it is a shuffling method. But our permutation and bootstrapping are pretty similar, but I do want to point out that this maximum is 1,250 and this one is 900, just to give you a little bit of an idea of where these things are coming from. As you can see, this graph resembles the theoretical distribution of the F statistic, but it is a lot more smushed down to 0. So that made our analysis more accurate because it was based upon the data we actually collected and not just the theoretical distribution.
So our result of our F statistic for our original data is 9.50739. And you can see on this graph, our F statistic would fall right here on the permutation distribution, and off of the graph here for bootstrapping, approximately. So both of these are extreme values given our null distributions that we found, which you can also see from our p-values. For our permutation distribution, we had a p-value of 0.001499 for the permutation
For that graph.
For this run through of our experiment, and then for bootstrapping, we got a slightly more extreme p-value of 0.00049997. Which means that given, if the null distribution is true, the probability of getting the F statistic that we did of approximately 0.95 is 0.1499 for permutation, and even lower for bootstrapping. For our bootstrapping, we also found the confidence interval of 0.000. There's probably some other digits there that wasn't picked up in our code, but it is a positive interval given the nature of the F distribution. And our upper bound is 3.233. This means that we're 95% confident that the true F statistic for the null distribution lies within this interval. So given that our F statistic is far outside of this range, we can say that it's extreme.
And because it's extreme, it's significant. Woohoo! So the surface really does matter with the water balloons, and that will help you in all your future water balloon activities. Another way to say this is that there is a difference in the mean splash diameters across surfaces, so that's pretty important. That difference in means is the F statistic idea. Okay, so we can conclude that surface does matter, and you should take this into account in your next water balloon battle. Thank you very much, and that's all.
Bye.